Hey, let's try again. Yes. All right. I forgot to turn the microphone on. Okay. Yeah, as I was saying, we're going to be working again on this SCTE 35 package that we're writing. It started off as a refactoring of a package from Comcast, but what we're going to do instead is, well, what we've ended up doing is just rewriting the package by deleting thousands of lines of code, removing all external dependencies, and kind of not just copy and pasting documentation from the spec. So I think that we can just get right into it because I think we'll just see like what people want to hear about in terms of background and stuff. I've put links to the source code so that people can follow along, and also I've put a link to the background info just in case, just for that kind of really quick summary of what it is that we're actually doing here. So let's just get right into it, I'd say. So where we left off, let's just review the spec. So we're working through a part of the specification. In particular, we're working on this particular message type, if that's the right word, but certainly at least the structure called a splice info section. We've just called it splice info in our code. So I'll just bring the docs up for that. And oops. All right, let's try again. There we go, there's our code. Here, streaming the internal package at the moment. All right. Here is our splice info struct. So specifically where we're up to, if I remember rightly, is we've been able to encode all of this stuff, and we are up to, oh, I can't actually remember now. Maybe this splice descriptor, I can't exactly remember. But yeah, let's have a look, see where we're at. So got our tests running here already. Splice info. So here's our big bad function. Encode splice info. So it looks like we're able to encode the splice descriptor. So it looks like the last bit is going to be encoding this ERC32. So there's a bunch of existing stuff already from the Comcast package here. What I'm also tempted to do is, I think we're just about ready to, yeah, I think we are, yep, we're going to delete the stuff from Comcast's, that we were using from Comcast. That's the splice info section.go, that can go. And I think this, yep, that can also go. Let's get rid of that one as well. And finally, here's the last bit from last bit of the splice info struct that we're wanting to deal with, which is this CRC32. So this CRC32, if I understand correctly, is a is it a checksum? I'm actually not sure. Let's just have a quick look what this is. Pretty sure. So it's like an integrity check. It uses so let's just see when we need to use this thing, because I'd be really interested in just trying to get a end-to-end test of getting a splice info, encoding it, and seeing if we get some expected results, because the we have some samples in this specification that we could use. So, and I have a feeling that we only need to use this check if the SCTE 35 messages are encrypted, or at least the some of the payload is encrypted, I think. Let's just review that. So first, let's see if we can, basically what I'm looking is if we can skip this CRC32 for now, just to get some testing, that would be awesome. Looks like my memory serves me right. So CRC32 is a 32-bit field containing the CRC value. Yes. Oh no, maybe we'll need it regardless. Really would love to know how they generate the table, but anyway. Containing all the bytes of the splice intersection up to the CSC cat CSC measurements. Okay, so it looks like we may just be able to use this just as is. Apart from this IO-bit new reader. So as a quick refactor, let's just not use this IO-bit new reader, because then we can fully delete this entire package, I'm pretty sure, from the whole module. So let's just quickly get rid of that. So what this is doing is creating a new bit reader from the input slice of bytes. But what that does, so let's have a look. Put this over here. There we go. So r.bytes. So we're creating a new reader. We're using the bytes method. So B -4. So where's payload actually used? There. What does the uint32 method do? Reads up to 32 unsigned bits in a big endian order. Okay, so maybe we'll just use this, because I don't think we need to. Yeah, we won't need to. We don't need to go back the other way around for now. We can just calculate it and use this hairy function right here. Definitely could do with some refactoring to see what is actually going on there. A lot of steps in one go there. SCTE table. Yeah, way too much going on in that one hit, I'd say. So, let's finish our splice info struct encoding by calculating this checksum. So do 32 equals. Oh no, we can actually. Let's just do this now. Let's see, RC32 buff. And then we'll need to length of a uint32, and then we'll put that. We'll encode our uint32. Oops. Into this byte slice. 32. Ooh, sorry, this is the first bit of code I've written today, so B, and then there we go. And then I believe we've finally finished encoding a splice info. Now we can actually check the thing. Oops, calculate. Let's test encoding. Whoops. So we've got a splice info test. Okay. What I'm going to do is read the specification and get our sample message. So time signal, that's an easy one. Oof. Okay. Ooh. So we're going to turn this data into a splice info struct. Try encoding it and then see if we get these values at the end. So let's just grab that for now. Chuck it in here so we can keep this open. Yeah, that's a bit easier. So the type, let's open up our splice info. All right, here we go. Make sure we can see that. Oops. Sorry, just working with. Great. All right. Decoded length. Okay, so that's not set. It's not encrypted, so we can leave that. The encryption algorithm doesn't matter. PTS adjustment is 0, so we can leave that too. The CW index. Can't see that anywhere in here, so let's just leave that 0 for now. The tier is OXFFF. To double check what that is, so whoops. If our splice info just chuck it right in, I guess. Okay, our command is a time signal. The time is that. Time signal. Okay, so it actually feels great to do this. And finally, all this hard work of just being able to specify this stuff as a literal and not dealing with the bits and the bytes. Yeah, it feels like hard work paying off. And so that value is that might be a, okay, so this seat minus here, that might be the PTS adjustment from the splice info. Anyway, the time is that value, so a time signal. Actually, first let's get this PTS adjustment. There's going to be some serious messing around here. Let's just see what happens. We've got a whole bunch of type conversion going on, and looks like that's our command done. So if we go back to our splice info, the next bit is going to be our descriptors. Can't remember what this looks like. Okay, tag. script splice descriptor, the tag. Not sure what exactly that's going to be there. Oh, sorry, this is a segmentation. Okay. Unfortunately, we are not ready to encode this particular splice info because I think what this sample is saying is that this is a decoded segment descriptor, which we have not implemented yet. So still no good. Still no good. Yeah. So let's delete this. And I think we may have to come back to it later or so. Yep. No good. We're gonna have to come back to that later. All right. So thinking what exactly to do next. It'd be good to, since we've decided to get rid of I think we can get rid of that too. So it's a UTC splice time. It's not actually used anywhere. So we can get rid of that. This type, I believe, is not used anywhere either. Okay, let's just do it one at a time. Let's get rid of that. Save that, and from now on, do nice small commits as we go. To put in, so with commit messages, this is something that might be worthwhile to all our thousands of listeners here. So what I like to do here is follow the same commit message sort of format that the Go project uses. That is the name of the package, or at least the path to the package, a description quickly of what the change is, and then as the body of the commit message, maybe a line or so explaining why, and maybe with a bit of reference, maybe some further reading that could be done. So here, the description of our change is remove the unused UTC splice time, type. Why is because in our new code, we already use, I think if I remember rightly, we have, nope, not there, maybe in command. Yeah, so we just use a plain time.time value now. This wrapper, because at the end, that's all that this type really was just a wrapper around time.time, which itself was only needed because there was a bunch of XML craziness going on. So no need. Another 18 lines down. Great. What a feeling. Okay. Other stuff that we can remove. Yeah, in this SCTE35 file, we've got here this byte array, which is, yeah, not needed. And this entire private descriptor. Yeah, again, we have implemented this in the, was it splice info? I think at the bottom. Yeah, in a splice descriptor. So, yeah, here it is. Encoding it is done in, yeah, very good. And the length, yeah, again, nonsense, we can just get the length of the slice. Let's commit that. Which file was it? Make sure we can compile. Nope. Oh yeah, and of course we just delete this whole file. Great. Again. Excellent. I'll save that for now. And then I think we're good. Separate out the commits. Let's just remove this. The What's the other bit? Okay. Great. Don't really need to assign a variable there, we can just do that. Calculate CRC32 is clear enough. I would even just call that CRC32. Okay. See if there's any other parts of IO bit that we can get rid of. Oh. Let's leave that for now. Okay. Next up, I think, would be to finish off the rest of this splice descriptor implementation. So let's have a look at the spec and just see what else we need to do. once we can encode all the different types of splice descriptors, then we can finally do a full encode test of our splice info section, which would be great. So, yep, these are the ones. Specific. So oops. So we've got our splice descriptor here. So it looks like there's a, as it says in the spec, a bunch of like specific splice descriptors. So this is probably a good little discussion point because there's the previous way that this was gone about was sorry, let's do this. Back. Ugh. Okay. Yeah, let's keep that there. Okay. So previously this was done by having a bunch of different types here. Veil, descriptor. There was the DTMF. There was the segmentation. Time. Audio. All of these can be described in terms of the splice descriptor. So the problem with having so many types is it just means a lot more code. And I don't think the types really represent I don't know, because these things can be represented with, let's say, yeah, yeah, I don't know, doesn't, because they're really splice descriptors, and the values of the splice descriptor determines these things, not necessarily the yeah. At least with Go, I think it's more idiomatic to not have so many types like that. It's not like Java where you got loads of classes, classes. It's not really like that. So let's see what we can do to find a clear way to work with all these different things. Okay, so it looks like what I'll need to do is it seems like, unfortunately, we're going to have to define a whole bunch of new types. Yep. Let's just review how the Comcast package did it. So, okay, let's just check out the old revision, I think. Yeah, okay, so again, this weird thing of using these uint32s instead of, yeah, it's just misleading. Yep. All right, so looks like we can, what we'll do is say in the example of an audio descriptor, let's just Yeah, we're going to have to do an audio descriptor and all that. So let's just check out the head again. Oh no, not head. The what are we doing? Name. And we'll go to our splice descriptor. Just double check where our existing splice descriptor is. Descriptor, where is it? Splice info. What we'll do is we'll put this into the splice descriptor file. Top there. Now let's go and define all of these. So knock that out. So we're not going to need that for quite a while yet. First one will be an audio descriptor. Looks pretty easy. It's going to be the all this is just an 8-bit number, so quite sure how to deal with that. Maybe save that one till afterwards. Okay, maybe we could actually just do something like this, and then move on. Okay, DTMF. Oh, sorry, my mistake. The DTMF is that. Okay, so it's DTMF descriptor, and then avail descriptor. Yep. Okay. Again, the only thing that changes is this fail descriptor. Sorry, the fail ID is just a 32-bit number. That's all it is. So I feel like we should just extend this splice descriptor. However, we'll just check the other descriptors, make sure we can't do that. So for now, let's just do this, a type of avail descriptor is really just a unit 32 and a DTMF descriptor. Oh, well, it's just represented by the pre-roll value. So look, this isn't great, but let's just keep going with it for now. Segmentation descriptor. Okay, this is a bit more meaty. Whoops. All right. Ooh. All right. Okay, back in a sec. Right, hey there. We were just looking at the different types of splice descriptors that we can get. So looks like look. Yeah, okay. Looks like we can just splice descriptor. Something like this. Count is a in a 3-bit. And then we've got the character. So comma is a as well. Or rather, just a byte, I think is clearer there. Yep. Citation descriptor. Now we may be able to use our event type in here because this looks quite similar. So let's just double check. Event, out of network, splice time. No, a bunch of other stuff in here. Is a 2, the, what's this, cancel, seeing whether these are flags for things that are to come in the rest of the structure, or whether they're actually themselves have their own kind of significance to the application. So this program segmentation flag, we can yeah, no, okay, so delivery not restricted. Okay, so we can skip the program segmentation duration. Yep. The delivery, and we can skip that as well. And then we're going to have a the next 1, 2, 3, 5 bits. So one, 2, 3, and device restrictions. We actually have some device restrictions. But these can be defined actually as just, rather than as so let's get these. This is going to be delivery restrictions, and that's going to be a 1, 2, 3, 5 bit field. So let's set this as a and we can actually set some constants here, because I know we have device restrictions already. Delivery restrictions rather. Here we go. So what we can do instead of all this stuff is actually do a const block. Let's do it here. Oh, let's do it up here actually. So delivery allowed. Is actually just the value 1 shifted to. So shifted 1, 2, 3, 4. And then we can just use iota. So 4 plus iota. I think that's right. We'll test that. No regional blackout. Archive cloud. Just check how to encode those device restrictions. Oops. not here. Device restrictions. Okay. So then at least device restrictions. It's going to be, this is where, so the binary value is going to be 1, 2, 3, 4, 5, 6. So it's going to be that. So then that'll be maybe 1, 2, 3, 4, 5, 6, 7. Yeah. And then group 1 is going to be yeah, like that. So be good to get that into a hex value, I feel, because so device restrict group 1. So just going to have to look up how to do this with hex. So I can just use go itself. Just do that, and then we'll could use a hex table, but yeah. So this value is a this is a so that's OX 40. X 80. I feel like I should be able to work this out. Okay, anyway. OXCO. Okay. I'd like to put that in one block because it's, yeah. And we can delete all of this now. So now when we encode yeah. There's a neat way to whether there's a neat way to encode that. For example, with a file mode, if there's a file mode, oops. And then we can look at and then if we say we look at FS mode, you can see all the different things that could be set. So I feel like I kind of like the look of that. I kind of like the look of that enough to try and use something that's standard in Go and in Unix and file system stuff to be able to set the flags neatly here rather than defining like a whole new struct. And again, like why use a type when just plain old values can do. So let's see. I'm wondering if anybody here can help me out here. Perhaps we really want a maybe a new type, just like this, called, instead of file mode, we could have something, yeah, like just delivery restrictions. Delivery restrictions, and that is an 8, and then something like that. Yeah. And then we could just don't, yeah, not sure exactly how this works, but anyway, since this is the leftmost bit is 0, and then the one next to it is 1, and this is 1 0, and that's 1 1, and then 0 0 0 0 0 0. So setting the flags would be something. So let's say restrictions here is a delivery restrictions, and then setting it would look something like this. So let's say, let's just do it in a new, just a scratch space just to see what it could look like. So let's say we have a segmentation descriptor. So desk is a segmentation descriptor, and then ID is, like 1 2 3 4 5, and then let's say restrictions. What we could do is we could just have restrictions equals, and now we can use bitwise operations. So let's say web delivery allowed and archive allowed, and then let's say device restrictions none. And then we'd set it like here, restrictions, like that. And then modifying again, you could just go device restrictions or equals, say you wanted to, set something, you'd say, oh, I want to set no regional blackout, so you just do that, no regional blackout. That looks pretty good to me. No, look at that much more. So yeah, that looks really good. Using the bitwise operations is, yeah, that looks really good. Okay, great, very happy. Great. All right, let's move on. So we've got segmentation descriptor, observed, segmentation duration. Okay, that's a 40-bit integer, which, let's see what that looks like. So I'm pretty sure we have a segmentation duration already, but in here, but let's just, pretty sure this is just going to be a presentation timestamp, which is what we deal with a lot. Let's just make sure. Segmentation, find this. Duration. Oh, okay, try again. Segmentation duration. 40-bit unsigned integer. Okay. Weird, because all the other ticks have been 33-bit unsigned integers. So it's okay. If it's 40 bits, that's okay, because that just cleanly fits into 5 bytes. So let's put a, let's set this value as a segmentation duration, as a pointer to a uint64, and then let's just say that it's a 40-bit integer representing number ticks of a 90 kilohertz clock. And I would like to just call that duration, because we've already segmentation descriptor, so segmentation descriptor, segmentation duration, ugh. A lot of words, unnecessary. Let's just see. Duration of the segments, yeah, okay. No, right, just duration. Great. UPID, okay. Segmentation UPID. So this looks like a whole new structure altogether. And we actually had this in Comcast's package, so it might be worth looking at that. Segmentation. Let's just format this. Let's have a look at the package. So let's go like this. Just find commit. I think it was, yeah, this one. Okay, so we'll just use this one to look at the old package. Oh, no, sorry, what's this? Oh, okay. Let me just check out all this. What was that commit? A27 there. Okay. And we're trying to find this segmentation UPID something or other. Here we go. type format identifier. Okay. All right. Few bits and pieces here. So looks like we'll get the we'll define a new type for the segmentation UPID, and then as we had before in the Comcast package. However, the type doesn't need to be uint32. It can just be a plain old uint8, and then and then we'll do a enum of all of these different types. I'm surprised this wasn't done before in the Comcast package. Not quite sure. Just see MID. Oh yeah, no, there it is. Yeah, okay. We might still have it in our current checkout. Let's have a look. MID. Nope. Yeah, but it looks like we could actually define a new type as a UPID type, and then string methods, all that sort of normal Go stuff when we're working with enums, which didn't exist before in the previous package. So let's I want to maybe a new file, because we're filling up this splice descriptor thing quite quickly. So segmentation descriptor will have a say UPID, and just see whether we need whether we should define a whole new struct, or just put the values as put new fields in this particular struct. Yeah, okay. Let's, in this case, segmentation UPID. I'm still not sure exactly what that struct looks like. Oh no, yeah, I do, like this. Value. Quite a lot of stuff here. Okay. And the segmentation UPID from table 22. still want to. Let's do it like this. Then the UPID is going to be this is not particularly clear. It's like a general sort of structure that contains a bunch of different things depending on what the type is. So it's almost like, yeah, I'm not quite sure how to represent this. So it could take a URI, UID, nothing, a airing ID, whatever that is. So yeah, quite tricky. Sure. To do a let's just start with maybe just enumerating these constants, because then at least we've sort of got something. So UPID type none equals this is a what's the size of this particular value? I think was a, okay, great. It's just a single byte. So type UPID type is 8. Here we go. Down we go. Oops. I think. So much stuff. All right, here we go. Thinking whether we skip out the deprecated things. Let's just do this. User defined CI. All this junk here. Add ID. Add ID. EMID. Hyphen. Oops. Now there was a way to skip over values actually. Was it underscore, I think? something in the Go spec that allows you to kind of skip over values even when you're doing an iota. Sure where that's found. I think if anybody knows what I'm talking about. Oh no, I think it was in the Go blog. They actually have they have an article about it. So it's just a neat way of, especially when you're dealing with things like this, instead of having to like kind of start again, you can just skip and then say, you know, have a comment about that it's deprecated. It's really good. A segmentation repeated type as defined in, let's get the section, 10.35, 10.3.3.1. Great. All right. Valid repeat type values defined in table 2. So actually it's just 2. And then once we get to OXOC, let's just put that here and then refer to it later. Okay, ISAN. TID, TI, ADI, TSC, content identifier. Content, let's do ID. View and ID, ADS, info, CR. And the sensible thing maybe would be to prefix this with UPID. Just because we've got to, it's tricky. Now here I feel like what we do is I think we might have to just use a slice of bytes because there's quite a lot going on in here. And I think it's beyond really what we want to implement, especially at this like early stage of, so. just fill in this. OXOC is use MPU. Any other deprecated? Nope. And then reserved. Oops. And this is also deprecated. Is ISCI. Yeah, it's harder. So I think now so we've got the UPID type, UPID length. Yeah, let's say a segmentation. I feel like we could actually have we're gonna have to have a type here, type UPID, and it's going to be type is UPID type, and the value is really just going to be a slice of bytes. That's all we can do. And then we don't need the length because we can just calculate that at when we're encoding, like at runtime. Easy peasy. So let's put this here, and then let's have a is a pointer to a UPID, I think, and we don't have to. No, actually, no, we don't need a pointer because we can just, because the value of 0 is okay, and the length then would also be, well, and then we've got a nil byte slice. So when we're encoding this or decoding it, if we get a type of none, then we know the slice is nil. So yeah, it would be okay. And the length is, yeah, if there's no segmentation UPID length is 0. Okay, easy. Okay, I'm happy with that. That's good. Okay. Segmentation type ID. Okay. Again, more types. Segmentation type. So UPID type. Segmentation type. All right, look at this. Look at this beautiful stuff here. Oh, so many values. I don't know whether we really want to define or like specify all these, but I think at the very least we can set the fields for it. Yeah, let's have a look. So the type is going to be a EU8, and the segmentation, segment number. possible. Down we go. Segment num, so expected. Just trying to get the, I don't like this num name. I don't think that's any good. So we're just trying to find a good name for this thing. I feel like count may be clearer. Each new segment, the value of this field shall be indicated as in table 23, which is what we just looked at. So I think that's saying support for numbering segments in a given collection. Yeah, so it isn't. It's almost like the, yeah, it's not the count, it's the, yeah, the like the numbered sequence in a collection, yeah, like an index. So, but let's say let's call this the segments. Call this the sort of the of this descriptor in a collection of descriptors. Expected is just the count, is that right? Yeah. I'm wary of adding comments that are not really useful. But I think those are okay. Okay, so again, sub number is a UN8, and that's going to be the numbered index of any subsegment. Yeah. Check if that's the segments or the yeah, let's just check. Okay, so this field provides a count of the expected number of individual subsegments within the collection of subsegments. Yep. All right, so what we want to check now is whether these things need to be pointers or not. So what we'll want to, I feel like we're okay because it's all going to depend on the value of the type here. So and all of that depends on okay, so okay. Great. And then I think, oh my God, I think we've actually finished this. Yeah, holy shit. Okay. Fantastic. Like to, at the beginning of these, just add upid. I feel like I need an underscore or something, but I'm not sure what exactly is I feel like I'm just going to have type. They're just long type. It's not great, but yeah, it's okay. Easy to refactor, very easy to refactor. All right. Next up is let's push what we've done already, just because then people can look at it. Okay, let's go to the next type of splices, segmentation descriptor. Yeah, splice descriptor, yeah. So we've done segmentation descriptor, that's great. Great. Time descriptor. All right, let's go down again. So we've got a time descriptor. Say TAI seconds. 48-bit number. So 48 bits is 8, 16, 24, 32, 40, 48. That's a okay. This will be a we're going to have to use a uint64. And then I wonder if we can use a duration. No, we can't. The duration doesn't go high enough. A duration in Go is just a 64-bit integer, signed integer. So yeah, so we're going to have to use a seconds. Is it 64? No seconds. Also a is just a unit 32. UTC offset is sure whether that. Okay, next up is the audio descriptor and the final. What would yeah, we'll just do audio descriptors really an array. Audio channel, audio channel is structure. Component tag. Okay, yeah, we'll need this here because it doesn't come. We can't get it from anywhere else in the splice descriptor. Language. Can this just be a decode column of the ISO 6392. Oh. Okay, let's have a look at how the audio channel struct. Again, not a great name. ISO code of what? It's the language. Right, so language is a string. From ISO 6392. Great. Okay. Again, bitstream mode. It's 3 bits. We're up to 3, 4, 7. Okay, so sunglasses on. Language. The channel count. This is a full service. To see how Comcast dealt with the bitstream mode, if at all. No, so they just read the bits and write the bits. So there's no specific values. That's okay though. holy shit. And then with that, we're actually at the end of the spec. I mean, the last bit is the encryption. But, I mean, a lot of that is, wow. Oh, jeez. So now we can get rid of all this. And we've taken a few shortcuts here, so let's just add some proper description of what is really going on here, because there's, yeah. I'm not sure what TAI is. Does it say anywhere, TAI? Interesting. So this is like a broadcast specific time synchronization protocol. Oh. Okay, so a 48-bit integer on of the number of seconds since when? Since So this is actually the representation of a precision time protocol time value, which is this its own thing, its own time synchronization protocol used in broadcast and AV and stuff. So that means that while this is called time descriptor, I mean, what we really want to do is maybe yeah, maybe just like in here, make a reference to that in the code, because yeah, it's I kind of think that would be clearer to put there. So God, this is weird. Okay, so time descriptor is a time for precision time protocol. God, the stuff you find yourself into doing this broadcast stuff. It's okay. So precision time protocol. So this is got to be the offset of seconds. 16-bit numbers using conversion of the following equations. TI seconds minus UTC offset. Yeah. Okay, so the number of seconds between NTP time and the international atomic time. The current difference between current the current between the same you know, it's going to be between something like that. So since the Unix epoch, so the number of seconds since the Unix epoch according to and then the same for nanoseconds is just the corresponding, you know, except I just need to double check that it's 32-bit, yeah. So it's not a subset of the bytes. So this will be the this is going to be this because you have the seconds and then the nanosecond denomination. Would that be the word, or? Number of, yeah, anyway, okay, let's just format this just so we get seconds dot just for now. Let's get this and TAI. A moment time as used in the precision time protocol. Uses international atomic time, TAI, so that we can use TAI in the descriptions. Yep. All right, that seems clear. And then I would really want to. Oh no, I think that's pretty good. And then here. Okay. Oh, I got somebody else watching. Hey there. Don't know if this is even interesting or what, but if anybody's got any questions or anything, just ask. Like, I'm just, you know, I don't think I'll be able to answer, but hey. Oh, no, even another person now. Hey. All right. So we're just yeah. If you want me to go over exactly what we're doing right now, happy to do that. I'm wearing sunglasses just because it's really sunny. It's sort of mid-afternoon in Australia, so and the sun's shining through. So okay. In a seconds. I want the, what's the word here? It's we have the number of seconds and then number of nanoseconds. I'm just gonna have to leave that like that for now. Okay, so if I've got that right, we've just done all of the possible splice descriptor implementation. So we've done a private one, which is just a slice of bytes. We don't care or know what that is. We've done this available. Let's go up here. Yeah, it's just a number. So actually we should document that. But anyway, DTMF, segmentation descriptor was quite big. Time descriptor is what we've just documented, and the audio descriptor is what we finished before to the bottom of this file. So that's great. Let's just see what that looks like in the docs, just sometimes like to read it just to see, you know, if everything kind of looks like it makes sense. Yeah. So we've got here audio channel, audio descriptor. I feel like we don't really need that. Since when we're decoding and encoding when we're decoding and encoding the splice descriptors, which is splice descriptor, we're going to have a is it in the tag? Yeah. So the tag will tell us what type we've got here. So it'll be time descriptor or all those other values. So it looks like I would like to document that because that's pretty unclear right now. There's probably going to be some constant values that we need. So the tag. Yeah, okay, so we've got DTMF. Yeah, okay. So let's get this order correct. So we've got the how to do this, a segmentation. This is a tag. DTMF is a descriptor tag uint8. So uint8 equals 1. Hopefully we can just use iota instead of having to manually go through all these. Available descriptor. Okay, great. So avail, so tag avail. We can just do iota and then knock out all this. Okay. we'll go down, segmentation descriptor. Hoping this is 2. Great. Okay, so segmentation. Fingers crossed this is 3. Great. Time. 0, 1, 2, 3. Great. Yep. Keep going. Audio. 4. Right. Tag, say identifiers. Because it doesn't actually specify, it's really specified by something else, by the data. I'm going to need some more documentation here, so what we're missing as well is the private tag. So we've done these val, DTMF, segmentation, blah, blah, blah. But if it's, like a custom tag, or like I'm kind of looking for a tag private, that would also be good. I think that would be clearest. Yeah, right. Okay, so it's identified. Okay, so all right, so we'll need to get the ID. To I think it's tag eval, and the so what we're saying is we're may be used to decode, or used to if the tag is one of tag val, then the types such as, yeah, so yeah. Man, this is some boring code. Just specifying it's all over the shop for this, like legacy analog tone stuff. Ugh. Like, I don't mind working with bits and bytes and stuff at the moment, but documenting this stuff is pretty boring. But it needs to be done, because what's going to happen is you write this code, you come back to it in 6 months, and the previous package just had it was just a copy and pasting of the specification. But that's no good, because then when you're doing this sort of stuff, you often have the spec document right there next to you. So there's no point copy and pasting it. I mean, why? It's not. Yeah, just give a reference, give a link. Anyway, I think just checking things I need to do, analog output of the device. It is an 8-bit. DTMF count the number of DTMF characters. Holding, specifying the number of DTMF characters the device is to generate. So let me just check if I've got this right, because if it's the count of characters, then I've done something wrong. Yeah, I have, yeah. Okay, so this doesn't even need to be here. This can just be almost a string. This literally just represents a phone number. So 0 to 9 star hash. So DTMF. This is really just a I don't know best how to encode this 0 to 9 star and hash. If anybody's got any tips, that would be handy. I guess I could just call it, use a string and then document the fact that these are the valid values, and then yeah, or because if it's 0 to 9 and then star and hash, I think perhaps an array of a byte slice might be easier, because a string can, in Go anyway, can be UTF-8 characters and stuff. So you could have, all sorts of weird things that are, yeah. Because then the length of, when we're encoding and decoding, the length of the string isn't necessarily, how many bytes there are and all this sort of stuff. So is DT like a dial tone? How do I make it easier? DTMF, dual tone multi-frequency signal. Wow. This is how this can ever be used in, or why this specification, I mean, how this spec is used to signal ad breaks in, in computers, modern operating systems. I mean, why are we looking at this? What a spec, eh? What a specification. Talk about legacy. I think let me see. Hold a dual tone DTMF sequence. DTMF. Star and hash, or pound as they say in America, right? Dual tone multi-frequency, DTMF. And what we can do is we can just link to this is dual tone. Well, how do we spell the dual tone multi-frequency? Right. I don't know whether I need a new line there. I'll just double check. But this is just so that we have a nice value in the Go documentation. DTMF. Yep. Great. Let's see if we can knock out the line. I don't know what's correct or not. Yeah. Okay. No, we do need the line. Okay. I'll take these off now. Sun's kind of going down-ish. All right. It holds. Oh, that's it. It's yeah. Okay. consist of and it doesn't, it holds a DTMF sequence. Yeah. All right. Jesus Christ. Okay. The number of ticks on the collapse clock. PID represents a segmentation UPID structure. What I'll do here is just 10.3.3.1. So the value field, so yeah, also hard to know how to document this, but this is the contents. Yeah, the contents, it'll be the corresponding contents for the given UPID type, something like that. Yeah, something like that, since we've got a whole bunch of possible values, strings, weird other compact binary encodings, other structs that are defined in the specification, all sorts of stuff. So encoded contents for this UPID type, something like that. we'll just reference a table here just so that, you know, anybody crazy enough to look at this. So table 22, 35, section 10. No, I've already got this in. See, table 22 of, you know. There we go. Whew. Okay, so we have specified all of the segmentation descriptors. So now we need to write some code that actually encodes the splice descriptor in its sort of, you know, wire format, which is this kind of compact, you know, representation with, you know, a whole bunch of bit, you know, smashing bits together to save a byte here and there. So it's going to be similar to how we did our splice info structure, which is splice info. Where are you? Splice info. So we similar to this. All the logic we had to do for that. So really, it's just going to be like one big, fat, boring function that just, you know, runs through. Let's find splice descriptor. Oops. Go through here, and what we'll be able to do is also provide some functions to be able to encode and decode these specific types of splice descriptors. You've got segmentation descriptor, time, avail, and some other things. So yeah, let's that thing's annoying. Anyway, so it goes. Sorry about the noise. Anyway, whatever. That's life. Seeing where best to start with this. Splice info, splice descriptor. This now contains no Comcast code, so we can get rid of that. It's going to be unmarshal. Okay, so it's, we're done with that. Oops. I'll put that over here like this. Hopefully that's clear. So we're going to start with our splice descriptor. This should be pretty easy because we're only, we're just going to extract the tag ID and that's it. So we're going to have to check the length before we get going because we're going to need at least 5 bytes. Yep. Easy. Now I can just safely just do let's just start reading the values out. So this tag equals a byte of equals 8 of the first byte, and then the ID equals can't remember how that encoding. So what we want to do is read a uint32 from the next 4 bytes. And here, yeah, easy, okay. So it's just going to be little endian. Yep, okay, so that's binary dot little endian dot uint32, and we're going to do from 1 to is that right? Yeah. Okay, and the rest is just the rest of the slice. So from 5 onwards, 5 onwards. That wasn't too bad. Oh, the buff. Yeah. Buff. Okay. And actually, we can happy to just do this. Like that. I think it's because we're really just assigning things, so I think this makes it even clearer again. Curious to hear curious to hear what you think, if anybody thinking about this sort of thing. No. All right, that's that done. So the contents of data, we can actually decode that stuff as well, based on the value of tag. So I was thinking, what would be a useful function? Now the one to do first, I think the best one to do would be the one that is in the best splice descriptor type to be able to encode first would have to be the one that's in the example in the specification, which I think, I can't remember what that is. It's a segmentation descriptor. So let's just do have any errors, but let's just start like this. So, oops. There's all the values that we have. Put this in here. All right, let's turn this into a we're going to want to turn this into a literal struct that we have. So that'll be encrypted. Time signal descriptor length. I don't know what this is, but whatever. Jesus. Opportunity starts, segment number. Great. Whew. Okay. It's silly representation, this, like, why just lines? I mean, yeah, this anyway, let's do a splice to no, there'll be a splice info test. Yep. Okay. Here is XFF. The command is a time signal. time signal, the value of the time signal field is going to be, oh, what? Time equals, oof. Minus 21. What does that mean? We've got that value, but then we've got this. So does that mean is that the equivalent value? Not clear to me. Let's just see. So we've got 1, 2, 3, 4. 1, 2, 3, 4. That's our command done. Go back up. Next up is our descriptors. Okay, our first slice descriptor. So, slice descriptor, the first one is a restrictions are going to be regional blackout flags, so no regional blackout. With archive allowed, which one's that? Just archive allowed, okay. Followed with 3. It's group 2. Whew, this is boring. It's Turner. Hell's Turner. Turner ID. Jesus. It's the TI. Identifier length 8, Turner identifier is man. Okay, so the value is that encoded as an array of bytes. So go 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Yep, makes sense. All right. and then 1, 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. Great. Okay. Next up, we are going to get the placement opportunity start. So that's the is that in the UPID or no? That's the we're in the type of the segment descriptor. Yeah, that's right. So if we go back up to our segmentation descriptor. Okay, so the type is a placement opportunity start, which is, as I've written, defined in table 23, just down here, placement opportunity start. OX34. Brilliant. I feel like I'll need to, I feel like I'm going to have to name all these constants because I remember using this in a, in a real system. So even if I just name all these things, it's and it should be pretty easy, just a straight up and down const block. Looks like everything is, all increments by 1 for the most part, and we can, okay. All right, so let's just continue writing this thing out as a, writing out our segmentation descriptor literal. Okay, so the segment number here is number 2 expected, is 0, so we can just leave that, and then the rest don't need to be defined or not defined. Great. Okay. So that's our segmentation descriptor there. Jesus. All right, so next up is, I'm not sure what this is yet, so we'll just go our splice info section. So the whole thing is a really bad way to represent a splice info section that they give in the spec. So we'll need to get our splice info here. So we've got our descriptors. Yes, we've done that. So the next is the SCTE, and we can just copy and paste that value. There. Woo. Okay. So our test would be to encode this thing and get the value, this base 64 encoded value that they give us in their example, which is going to be this thing. So, bang. So at the end, that's what we want. Now, if we don't get that, well, that's fine. Whatever, shit happens. So what we'll need to do is be able to encode this segmentation descriptor, which we cannot do yet, but let's do it. 4, 5, 4, 5, 6, 11. One, 2, 1, 2, 6, 10, 11. Yeah, we know we need at least 11. Descriptor length. I'm not sure what that actually is. Oh, we don't know what the length is yet. Okay, so our next one is going to be our identifier, which is just the in our case is that constant value that I always forget the name of. No, it's plus info, is it? Yeah, we here. The QE descriptor QE something or other. I can put in the docs. I feel like that could just be a string, and then it might be easier to split up into bytes. So that's all we ever really needed to do. Because C is, let's forget this, table, yeah. 67, x. Yeah, well, okay, yeah, of course. Much cleaner. There we go. So now we're up to going through, where are we up to? CUEI is 4 bytes, so dex 2 plus 4 plus 6. No. CUEI is 4 bytes, so that'll be oh no, we don't need any of this shit because we're going to have a segmentation descriptor after that. So, okay, so now we're really starting actually at the beginning. Okay, so file vehicle we know we're going to have 4, 5. Right. All right. Put you in 32 into the into that thing. Yeah, so that's all right. Okay, and then Okay, now onwards to encoding the delivery restrictions, which is pretty easy because that is just a straight up uint8, which will fit neatly into a byte, but only if we have this cancel flag set. So if now we're going to go down and just do all of this. So buff, now one will need to append because we've already hit the limit here. So is append the byte of sc dot restrictions. Let's keep this open. All right, the duration. To double check. Oh, no, sorry, no, happened too quickly. So the next byte isn't the restrictions, it's going to be, yeah, we're going to have to set some flags first. Okay, so program segmentation. This should always be set because the other way is deprecated. Actually, I think I was reading in the spec. Yeah, if program segment flag equals 0. Yeah, so we're going to ignore that case. So we'll just set it always. So let's go back up the page. Move this along to here. All right, so program segmentation. So we're going to do. And then you byte into the buffer and then go here. All right. There. All right. So we know we're up to index 5. Assume we do not support component mode. Okay, if c dot duration not equal nil, then we go buff equals 6. Now with this one, we just toggle the entire should be right. I'll just double check the restrictions. Okay, so we can now go if not equals 0, then we can shifted to 5 and then assign the whole entire thing. Yeah, that's it. Poof. Okay, we're going to get the we're going to convert our what have we got, a UN64? Duration, yep. So we're going to turn that into a so we're going to turn our UN64 into a 40-bit integer. So let's just create a we can use that binary encoding, the binary package in Go. So let's go there, encoding binary. Let's grab the, we're going to do big endian because that's what's defined. And then, so we're going to do binary.big. How to append 60 into a byte slice. I don't know whether I need to allocate more, allocate damn, yeah, I can't remember how to do this. Put you in. Yeah, okay, what I'll do is I'll just, let me give myself UN64, so it's 8 bytes. Self-explanatory, but anyway. Oh yeah, hey, some more people watching. Hello, hey, how's it going? If you want me to, yeah, if you're interested in what's going on, just say hey in the chat or whatever. Easy. Okay, so let's do binary.big and put a UN64 into there. Oops. Dereference duration. Now we only want 40 bits, which is 16, 24, 32, 5 bytes out of that. So we're going to append bits, just 5 bytes. So B Looks good to me. So just double check. Okay, we've done that. Next up, we're going to need just to add a few more bytes. So okay, so we're encoding the, I'll just show you which type we're doing well, we're doing the segmentation descriptor. We're up to the UPID here. Rest we just so we've got a byte slice, and what we need to do is right now we're up to giving the length of the byte slice, which is pretty easy. So just 8 of the length of the that. So we've got the upid.value. Easy enough. Are we done there? Oh no, one more. Okay. Okay, great. So what's next? Type. Easy again. I could actually like pre-allocate here to save some memory, but whatever. We're not, this isn't for performance. If we were really doing performance, we'd write this in C, but we're not. We could do this in characters here. Could just do anyway, like I said. Now I just need to double check whether we actually put all of that stuff in, because that might depend on the type of the type field of the segmentation descriptor. So yeah, because I remember that from reading the spec. So let's just see. So we're going to go to this segmentation descriptor and then just check if it's 0 or oops, sorry, I'm just trying to see that. Okay. Subsegment num. Ugh. I think I might be okay in just leaving it out. Like, as in, yeah, if it's 0, then no big deal, which would be great. Sorry. Right. Yeah, no. Okay. So I'll need to. All right. Yeah. Okay, so I can do segmentation type and then start comparing those values. So let's just throw in the segmentation type, the number, and the expected. We know we can do that. We're about to do that, and then okay, done that, and now we'll need to do some checking of the values. So now this is the bit where it'd be good to have some named constants, because like this doesn't really mean anything. And I haven't named the constants yet, so I'll just, yeah, all these. Okay, so I think for now what I'll do is I'll just I'm gonna copy and paste these values. So I'll just do a switch statement and then just start enumerating all of them and then encode the encode it from there. So I'll just do x34 30 so boring, and then we'll just add a to do here that lets us know that we'll get back to it. Oh, hey, there's some people here. Hey, if you want any info on what we're doing or just anything, just ask in the chat, or yeah, anything. This is become a bit of a mission that we're working through here. Just check out type sub number. Sub expected. Is that right? Okay, I'll just do a to do here. This be yep, that's fine. We'll just do that for now. Okay, and then we've just done sub expected, so looks like, just double check the spec to see what else we might need to do. Oh no, that's it, yeah. Whew, holy shit. All right, so now we can just, now that we've encoded everything, we need to come back and, oh no, sorry. No, that's it. So we'll just return buffer. And then because this segmentation descriptor is a type of splice descriptor, what I really want to do is yeah, maybe no, not done yet. So I need to do these 3 fields at the top, which I've already done because we've done encoding of a splice descriptor, which has these 3 fields too. So to reuse the code, we can just now have a splice descriptor. So do splice. And we know from the work that we've done, we've got tags already. So the tag is going to be a segmentation descriptor. That's the type that we're doing, and the ID. Let's just have this up. Splice descriptor. Yep, and the ID is going to be okay, yeah, UN32, yeah. Anyway, it's going to be the constant of, I don't know whether UN32 is really the right thing to put there, because the most common value is actually a string of, which is a string of exact length of 4 bytes. So, let's do the ID is so we have our yeah, so binary dot little endian of 32 of the script of this constant of which is a description something or other. What is that description? Okay, our splice descriptor data is buff. And then finally, we can return, so the splice is that, and then we can return the encode splice descriptor, pointer to splice. Oops, what are the values of those tags then? Whew. Okay, be back in a sec, just going to the loo. Oh no! Oh my god! I've had the microphone off for ages. Fuck. Hey, Step. Thanks for telling me. That's fucking computers. Hey, computers are so annoying. Anyway, all right. So we want the yeah, and I was actually saying, oh, like if this is really boring, like there's a few people in here watching, so if anybody wants to like talk about something else or go through something else, or if you want more info on what I'm doing, yeah, just anything, just type in the chat. Yeah. Right now, I'm just getting the value out of this byte, which is 1, 2, 4. So it's like skip that and then right? Yeah. So that as a mask is is that? Yeah. So this is the value here. So we'll want that. So we skip. Yeah, it's cool, isn't it? Yeah. It's good to have some green. Thanks. All right, so where was I? Ah, yeah, skip. Okay, so let's skip. Yep. Okay. Section length. I don't really care about that either, so we're going to move on to also anybody who's watching, I might just push. What I'll do is I'll push the code that we've done so far. So let me just so if anybody wants, track along in their own editor, we can do that. So let's just do that. Let's do this here. Great. Okay. I actually should have, man, I really should have. I was doing these small commits for a while, but I got lost in it. So let's see where we're up to. So what this is okay, so the first commit will be also removing the oh no, okay, damn, yeah, I should have done that earlier. Anyway, we're going to commit decode text. This is probably the only diff that I think is okay. Right. So let's do our, oh no, sorry. Let's get this right. Let's get our, splice info. Okay. Let's start adding the decoding stuff and doing really small tests, like almost like a byte by byte testing of decoding something that we know is a good, we know is a correctly encoded value, correctly encoded splice info. And we'll just test our logic byte by byte, bit by bit. So is that done? And then we'll just add this to the test file, which is going to be here. Okay, and then I'm going to have to just do a to-do here. Because we don't know what that is going to be yet, but that's okay. Okay. So we've done subtype encrypted. Okay, so let's move on. So the next, so we've got the SAP type done. Section length we do not care about. We could, in theory, if we wanted to like optimize some memory allocation stuff, but yeah, you know, the Go runtime can take care of a lot of that for us. We can just throw loads of bytes at it. It doesn't matter. For now, anyway, let's just keep it easy. So we've got 4 bits. That takes us to 16. So we want to skip over to the next. Which byte will that be? So this takes us to 1 and 2. So now we'll go on to the next byte. So that'll be where are we up to now? So we've got 0, 62. We'll go. Oops. Oh no, again, we're not even storing the protocol version either in our struct. So what I mean by that is in our splice info, we don't even care about the version because again, it's a constant value. It's always 0 in the specification. So if somebody sends or tries to decode a splice info that's got a different version, I mean, you know, something for later. Nobody, you know. Okay, so again, as it's always, as it's a constant. Okay, so we've got skip version in buff 2. And then skip 1. Next up, we're up to index number 3. And we're going to check if this bit is set. So that's going to be, yep. So, oh geez, I can't even remember how to check if bits are toggled or not. I've been so many setting bits, I can't even remember how to check if they're toggled. If anybody here can remind me, that would be cool. But it's like if can I check against a value, or I can. If it's the I think it's this, isn't it? So OX well, I mean, because what we really want is we've got the leftmost bit. That's the one that we're setting now. Let's check. Oh, we're checking. Yeah, because we've already done a whole byte, so we're up to, okay. If that's the case, then we can read the next 6 bits as well. So I believe we would have to store that as a uint8. Yep. Okay, so we'll just do that, and then info dot. Oh, in a sec. Okay, so and then we can also go the next 6 bits. So that's dot encryption algorithm is going to be the value of the this, then masking off the first. So we're gonna again masking the leftmost bit and also the rightmost bit. I don't know if that's the right way to describe them, by the way. So yesterday we had a few really helpful C and assembly and Rust programmers in here helping me with this stuff. I think, so we want the values out of 3, 4, 1, 2, 3, 4, 5, 6, and that. So we want that. So that as a, yeah. Yep. Is rightmost bit is left for the rightmost bit is used by this 33-bit integer. So we'll just do by PTS adjustment. All right, there we go. So let's just test that. Just that on its own. We know the values that we want. Even though well, actually, no, we can't. It's still not enough, because the example that we've got skips, well, rather, in our example, all those values are set to 0, or their defaults, which we ignore because they're constant. So the part that we need to get to is the tier, which is down here. That means we need to extract the 33-bit integer out of PTS adjustment, which we can do. Okay, so the PTS adjustment is represented by a 64-bit unsigned integer. So let's start getting the bits out. So our so we want to check if the the rightmost bit in that byte is set, is toggled. I'm just gonna have to be really dumb here. I actually did this a couple of years ago, but I cannot remember, so. Yeah, you check if it's 0, yeah, okay, so. this one is going to be, yeah, just shifted the rightmost bit. So it's just shifted once. And then if that's the case, then or alternatively, we could, I'm just thinking of the clearest way to do this. What we could do is this 33-bit integer is to get that out, we're going to need 5 bytes, and what we're getting here is like the first byte. So we could actually just like allocate an array of 5 bytes and then just start throwing them in. Yeah, of course. Yeah, this is okay. This is the simplest thing. Okay, so we're going to do like a, so this is going to be actually an array, a slice of what did I say? 5. Yeah. So yeah, and then we just throw the bytes in that we've got. So that is now we're gonna have to mask this one just because we've got the and so this is the rightmost bit from we've already got that up. I think that's okay. And then, I mean, this is pretty boring code, but let's just write it like this for now, just to give me a bit of thinking time. Yeah. All right. So we've got our 1 for 5. Okay. Let's get the uint64 out of that, which is PTS, PTS adjustment. Equals by dot. It's the Indian now. Happy with that. CW index, easy, it's a single byte. Beautiful. Oh, hey, somebody followed. Wow. Thanks so much for... I don't know how to... Sorry, I'm really new to Twitch and all this, so... Oh, yeah, right. Okay. Thanks for joining us, Primate Verdun. And also VanStep01, thank you very much. Thanks for joining us. It's makes it a lot easier doing this with some other people, so that's awesome. Thanks so much. So that's the next bit done. What have we got next? So we've done our CW index. Okay. Next is finally the... Oh, no, you know what? I'm going to have to check this because we might be working with a bit field. Oh, no, we're all good. Yep. This is 12 bits. Okay. So our, let's get this right. Tier. So equals dot 16 of, oh, sorry, you mean 16? Is that right? I can't. Yeah. Okay, so we're gonna get the 16-bit integer out of the next 2 bytes, but then we need to mask it because we're only meant to have 12 bits. So let's get that. So it's 9, 10, is going to be the mask is going to be everything but the rightmost 4 bits because we've got 12 bits. So and then the rest are used by the next field, which is the, I think the length of the command, yeah. So command length. So if anybody here can help me with the hex for this, so say the 12 bits, 12 leftmost bits. So I know the first is going to be that, and then again that for 1, 1, 1, 1, 1, 1, 1. And then we've got for the next, like the remaining 4 bits as 0. So does that just mean it's 0? I'll just check. Oh no, I can just read. I've got a little. So instead of running the, like play.golang.org or the, the Go playground, I just have this little thing running, which so let's print this. 16 bits. Yeah. Cool. Okay. Great. That's it. Keep that down here somewhere. Whew, whew, whew. I cannot believe people are watching this. I cannot believe I'm doing this. I can't believe I'm writing this stupid specification. But as I said, like, it's a good, I think, software engineering exercise, because when we compare, I think, this package to the package that we found off the internet, I think we're going to see some, some big differences. Yeah. Anyway. Shit. So we're going to do info.tier equals. Am I allowed to do like that? But I don't know if that's valid. Anyway, nah, let's keep it simple. Split it out along the lines. It's totally fine. Okay, so we've got our tier out. Right, now I think we're good to return, we're good to test our, just until we get this thing compiling, right? Encryption algorithm asks, this is, yeah, so we use a few. Okay, so now we can finally that's the oh no, I still can't quite. Anyway, it's good enough. Let's test this thing out. So we'll grab our base 64. So, and then just check. Creating the base 64 standard. Decode string, yeah, that's it. So standard code. Just chuck that in there like that. I think that's fine. Okay. We can just totally bail out at this point because we're going to decode splice info. Okay, so now we'll try and decode that and see if we get what we expect. out. Let's just print this. Let's just print this thing out just to see what we're getting. Panic. Okay. Where are we? Where are we panicking? So it looks like, oops, where are we? Let's do it again. Splice info, here we go. Oh yeah, because, yeah, okay. So we're trying to get a uint64 out of 5 bytes. It's not enough. Oh, no. Oh, no. Splice info. Oh yeah, of course. I've got this is to I always get these slice indexes wrong. 11? Okay. Okay, so what we've got, no, that all looks absolutely correct. So what I can do is just grab a oh, sorry, wrong file. Okay, I'm just going to grab the known good literal and compare. So I know that this is a good value. So this is and then okay, here we're just gonna fudge it there. Time signal will get that as well. Again, these values just come straight from the specification. So they've given us a couple of examples with base 64 and also with them base 64 encoded. So we're just testing if we get what they get. Decode splice info. We wanted but we got that. Okay. Okay, well the first problem is that our tier is totally wrong. So we know we want a tier of that value, so we're not doing our bit mask correctly. Which is strange, eh? No, still not right. Let's go really simple. Let's just start by testing the tier. So if our, what's our tier? It's not info.tier. Let's do a hex. So this is me showing my serious inexperience with doing binary level stuff. So I feel like there's a couple of things wrong here. Let's do that. No, it's definitely wrong. So maybe, does this seem to be little endian? And then let's say I do that. No, okay. So I might be missing some might not be skipping, or at least I might be somewhere incorrect along the bits. So a few people watching now. Guys, got to help me out here. What I've got wrong here is I'll just show you the table. So I'm zooming along here and I missed, I'm not decoding these 12 bits correctly. So, and I don't think, look, the code isn't, probably the coder isn't quite clear enough. So let's keep going along. So yep, so we do, sorry, let me just get this right. I don't know if you can see that. Yeah, we'll just, there we go. Clear enough. Okay, so we're doing here the sorry. Okay, resliced. We're getting out the SAP type. It's just 2 bits. Skip the next byte. Although we should actually get the length, but anyway, we'll just do that afterwards. Let's add it to do there. So that'll be really handy because then we can just check the length of the buffer that is passed in is actually the length that we're told it is, and then just error out otherwise. So that saves us having a bunch of panics all over here. And it's actually it's 12 bits, so it's in both those bytes. Okay. So from here we ring 6. Yep, seems okay. So 3. Yeah, again, seems okay to me. So 1, 2, 3, 4, 5. I think I may have got it here, so the issue is that we're going from so we're getting that byte, and then we're doing 32 bits. No, that's right. Yeah, okay. I might have this indexing wrong. So we're going, what we want is, yeah, I've really got this indexing wrong. So we're going from I'm gonna have to always looking up these slice index things. Always. Just such a simple thing, but slices. No, where am I? So we've got an array of 6, so the slice from 1 to 4 I would expect to be 1, 2, 3. There you go. So have I got this right then? So I want the next 2 bytes. I mean, shit, like, if this isn't obvious enough, let's just do this. Line, yeah. That's all. That's all we're doing. So let's okay, so maybe this, okay, maybe that value isn't really, when I print it in, let me print it out as a decimal, because I know that the max value cannot be greater than 4095. So let's just check. So just reading this thing about the tier. This field may take any value between 0 and FFF. See that? Yeah. There's something about Indianness that I'm not understanding here. Oh, I know. So the bytes that I want, I think, are actually like this. So that, nah. So I want them the other way around. 9, 10. That's little endian. And then maybe I need that. No. Okay. This is good. So this is a good test, getting super fast feedback. Too bad I'm an idiot, so I can't work this out. But it's 6:30 p.m. here in Australia, 18:30. So could be of help here. Yeah, this is actually a good use of ChatGPT. Yeah, this is actually one of those things. So I can ask a very specific question. Yeah, might have some weird things wrong, but I'm gonna have to go, because it's I was actually meant to meet a friend half an hour ago. Whoops. But yeah, thanks for joining, whoever's here. As I have here now, like if there's anything that, anything that you want to see that might be interesting. Oh yeah, there's my friend calling. Hold on I'm gonna silence that. Yeah. But if there's anything that you think might be interesting, or anything really, just write it in the chat now, or no worries. I'm going to be back again in about 12, about 14 or 18 hours. So I think I put a schedule in Twitch, if that's the right. Yeah. So yeah, I'm just going to keep going with this. But yeah, thanks for joining me. It's makes it so much nicer to do all this stuff. But yeah, I will. I really want to do this. No, I really have to go. Yeah, thanks everybody. And yeah, I'll be online tomorrow. So if you want to follow, then you get a. It says that you get notified. So yeah. Cheers. Oh yeah, thanks Moses. That's good. Yeah. I need to follow people back. I think that's what I need to do as well, because then I know if other people went online. So I'll do that, and then that. Yeah. I really want to do this. No, I really have to go. So close to getting that. Anyway, yep. Thanks, Moses. All right. See everybody. Thanks, Primate Bernard and Van Step, and whoever else is out there in the big wide world. Thanks again. And I'll see you if anybody wants to join. I'll be back again in about, like 14 or 16 or 18 hours, something like that. I'm not sure what time zones people are in. Okay. See you. Bye.